Hi and welcome back to a new video. Today we are in Czech Republic visiting the manufacturing of plated. If you've seen our Computex booth footage, then you probably already know what this is about, because in the past years we spent a lot of time investigating new types of coatings for our water blocks, because we figured out this is not just an optical thing, but it is also absolutely relevant for its function, especially for corrosion resistance. And then we came along PVD coatings. And then we thought, okay, which vendor can we go with? And we went with Plated. And today we are here in Czech Republic visiting their manufacturing. So I can already show you the machine type which we will be using. And this is also going to be, or this is the biggest investment we did in the company history of Thermal Grizzly. Just because your data is stored on a server in Europe does not automatically make data protection simple. With US providers, the Cloud Act can still be relevant, even if your data is hosted in Europe. By choosing a German provider like Hetzner, you rely on GDPR compliant solutions and German data protection standards. For example, Hetzner Object Storage lets you store data flexibly, securely and scale it whenever needed. If data protection matters to you, you will find Hetzner's link in the video description. New customers can save $20 with the code DERBAUER20. PVD stands for physical vapor deposition. In this process, an extremely thin but very hard coating is applied to components, for example, traditionally milling cutters, drills, or in our cases, the water blocks. This process takes place inside a vacuum chamber, which is necessary to have a controlled environment free of, for example, ambient air and moisture. Inside the chamber is the so-called target, which is the coating material. That could be, for example, titanium, aluminium or chromium. In our machine, this material is released from the target by an electric arc, basically small lightning strikes, and they are turning the metal into vapor. Additional process gases such as nitrogen are introduced into the chamber. These gases will react with the metal particles and create special coatings such as titanium nitride or chromium oxide. In short, material is vaporized in a vacuum, activated in plasma and deposited on our workpiece, which in our case will be the water blocks. This is the PVD coating machine. This is also almost the same one as the one we bought. This is the Pi411 Plus G3. We bought the G2. The G3 has one more technical aspect, a newer technology that we don't need. That's why we went with the G2. And just from how it looks like, it's a nice looking machine, but you can't really understand what's going on inside. Just on the left, you have a vacuum chamber that's inside. That's where the parts are being processed. And everything behind me right here, that is where all the electronics and control units and everything will be inside. The cool thing is now, because this is how you would see a PVD in the normal condition, you can't really see anything. But we will get the chance to also look at one of the machines that are partially assembled, which means that we can also take a closer look at everything that's on the left from the vacuum chamber and also from the electronics in the back. So that will be super interesting. And then later we will come back to this unit and it will be open, and then we can take a look inside how it looks like when it's fully assembled. Now we are in front of a partially assembled machine. On the left, that is the heart of the system, the core, which is a huge vacuum chamber. On the right, that is where we just were in front of the machine. This is all the control and PSU and all these kind of things, so the electrical components. But we will first start with this side, which is, as I said, a big vacuum chamber. And usually you would have your parts sitting inside here. They will do rotating motions, so they can be hit by the material from all sides equally. And then on the left, what's missing right here are the targets. And those could be any kind of material that you want to use to deposit onto your parts that are rotating in here. And what you also have to do is heat them up to the designated target temperature. That could be anything between, let's say, 200 to 500 degrees Celsius. This highly depends on what kind of coating you're using and what kind of material you are using or like your part material. And that's what those heating elements are for. You also have challenges because you want to heat up the parts that are inside, but you also do not want to coat those heating elements, because you have to know that if you coat anything in here, it will always coat the entire chamber. So later on, there will also be covers on top that are protecting those heating elements. And at the same time, what you also don't want to do is heat up the entire chamber itself. So it's not just a very solid piece of steel, but it's double walled basically, and you have some coolant, some water running through to keep the vacuum chamber at the target temperature that you need. And usually, I would say as low as possible, because you obviously don't want your vacuum chamber to run at 500 degrees Celsius. That would only be necessary for the parts that are rotating inside. We were just talking about process gases that are being supplied to the machine. And here we have 2 drill bits that you will find just commonly, especially these types, somewhere online or in a DIY store. And they often come with those gold type coatings that are being on top. And you might think, is this even gold plated? No, this is actually titanium nitride. Then this is a slightly different color. And this is if you have titanium nitride and then also add aluminum. And that's how you can have different colors. Now this is the super interesting part, which is the cathode, or you could almost call it the raw material that you're using for the material you want to deposit. And in this case, this is titanium raw material. This is also quite burned already, but you can see this is in a silver color. Now going back to our drill bit, this is titanium nitride. So you added nitrogen into the chamber as well. And with the process gas, you can then not only have a pure metal coating, which you can obviously also do with titanium, but you get a titanium nitride coating. And with this, you can have all sorts of combination, different metals, can have chrome, aluminum, and then combine it with, as I said, different process gases. And those could be, as I said, for example, nitrogen or also oxygen to, for example, create a chrome oxide layer. The machine that we ordered is using 3 of those cathodes. So it's almost the same machine as this one, as I said before. And you can see in the door, it has 3 different ones. This one on the right is also titanium. This is, I would assume, either brand new or almost new. And you can see the surface looks a lot different. But it's the same thing that's inside, only with difference that this one is already quite heavily burned. And that's caused by the arc that is hitting the surface constantly. What we didn't see yet in the earlier partially assembled machine is the carousel that is sitting now inside here, and it's doing this double rotary motion. So first of all, this big carousel itself is rotating, then you have those small satellites and they will also rotate by themselves. So you can have the parts sitting inside here. This will look a bit different for our machine because we have much bigger parts and they will just hang in there and then be able to rotate like twice around their own axis. This is especially important so the parts are being hit from all sides equally by the material to form a uniform coating. That's how it would look like. That is obviously more for typical drill bits or end mills that you're using CNC manufacturing. This is also mostly where this technology is currently being used. To go back to the process itself, so we have the carousel inside that can spin, that is containing our parts. For that we need the base is the vacuum chamber that I explained before, and also the process gases. So this is kind of counterintuitive, as I said before, but the key is that first you load all the parts inside and then you're pulling a vacuum. And you have to imagine that this vacuum basically means that there are no other particles inside. No humidity, no moisture, no other gases such as oxygen that you would have inside the ambient air. All of this has to be fully removed, evacuated out of the chamber. That's why the vacuum is super interesting and super needed. And then you would, once it's closed and everything is prepared, you're heating up the parts to the designated temperature. And then you're using the cathodes, and here you have to create the arc on the surface to release the metal ions. And this arc is being generated inside this entire field. And this works in a way that there is a big current that is put onto the cathode itself. And then there is this small arm, a small lever that is hitting the, in this case, titanium surface and is igniting the arc. And then the arc is staying on the surface because the rod, the cathode itself, is not empty, it's hollow, and there's something inside to create a magnetic field that contains this arc on the surface. And by doing that, it's releasing the metal ions, and the metal ions can then flow almost freely towards the material you want to, like in our case, a 5090 cooling block, where you want to create a nice coating. In addition, you have a voltage onto the bias voltage onto the carousel, and this voltage is basically attracting the metal ions from the cathode towards the material. And that's how you then create your coating. Also, just looking at the machine, it reminds me of the first time that I saw this machine at an exhibition, and already there I was thinking, this looks super expensive. And if you're wondering how expensive this is, It is more than €1 million. I'm not telling how much exactly, but a lot more than €1 million. And just going back to this, I want to show the arm that is igniting the arc on the surface. What is also another thing that's super cool about this machine, so if I touch these buttons, the cathode is rotating, as you can see. That is also a very unique feature about this machine, because this arc is not constantly hitting the same area on a simple target, but because it's rotating, it is hitting basically the entire rod. And that has a huge impact on the quality of the coating that you're creating. And this also explains, if we go back to this one, why this one looks the way it is. That is also a question I had earlier, like why do you have on top and of the bottom a bigger wear on the cathode? And that's because you have it just across the cathode like that, and the way it's traveling on top and bottom is simply a bit longer or larger than on the entire rod itself, and that's why you have a bigger wear on top and bottom. The effect on the surface that is caused by the arc itself is also dependent on the material. On the left, you can see the titanium cathode that we looked at already in the past. And this one on the right is a chromium one. You can see there the pattern looks completely different. Earlier I also had a super interesting chat with one of the R&D guys from Platit, and there I just realized once again how little I actually know about this technology. And I'm just trying to explain this as well as possible, but there's so many effects that go into just making this technology work. For example, what I also left out is the argon etching or the metal ion etching that is used before the coating. So once the pieces are inside and before you start with the coating process, you still have to clean them, and for that you can use like an argon ion etching process or like a metal ion etching process where you use some of those titanium metal ions and shoot them onto the material to clean it, remove it from like oxide residues. There is a lot of crazy stuff that is happening inside there. The process itself is also super clean. That is one thing I like about the PVD coating. The main consumable, aside from a few of the process gases, are those metal targets, and it's just a pure metal, especially compared to, for example, the electroplating of nickel. This is a much more clean process, and once this metal target is consumed, you can just get it reworked or get a new one. During the coating process, you also have some sort of dummies sitting inside. In this case, it's triangle shaped, can also be round shaped. That's probably what we will use. And this is placed inside at the same time to be able to have something to validate your batch. So after each batch, you take out the dummy, and then you can perform testing on the coating itself to, for example, check adhesion, hardness, and see if everything is the way it should be. And how this works, we're checking out in the other room. To test the sample, they use a calo grinder, which is a super simple yet effective technology. You have the triangle, our sample, sitting in there, and then there's this small bar in front that will rotate, and on there you will have this metal ball, and this metal ball will grind. It will be driven by the bar itself, and it will grind on the surface of the triangle. What's then happening is that you have a spherical grind shape into the material, which you can then later on investigate under a microscope. That is the process. Depending on the coating and the material, this can take a few seconds up to a couple of minutes. Then, next step, place it underneath the microscope. That would be your picture underneath the microscope. The very bright circle in the center, that is the material underneath the coating, and everything between this blue line and this blue line, that is your coating. And because you know the diameter or the radius of your sphere, of your ball, then you can easily calculate by knowing the difference in diameter of those two, or radius, you can calculate the thickness of the coating that you deposited. And this is a super simple yet reliable technology. And that's also what we will do for each batch to test the coating of our products. So much with our quick journey to Platit, to just visiting their manufacturing. It was absolutely impressive. I was also able to see a lot more than you could see on camera, because obviously with such a high technology company, it's always a risk of showing certain things. That's why I'm super grateful, and thank you very much, Platit, for the opportunity, for me being here, seeing all of these things, and then even being able to show certain things also on YouTube. For example, now standing next to the 1011, that's one of the bigger machines, they call it the workhorse. And for example, there is a small window in front where I was able to look inside and see the argon plasma that is used for etching of the surface, preparing this, like basically cleaning. And when in your life do you have the opportunity to see an active argon plasma? So yeah, it was a super interesting day for me. I hope you also enjoyed this video. See you next time. Bye bye.